Morning, good afternoon, and good evening, everyone. So today we're going to be continuing our calculus series, and we're going to go over some conceptual problems related to the things we've discussed or it was actually just yesterday. But we're going to do some stuff related to span and vectors, as well as linear systems in general. Matrices, same thing. So let's just hop right into it. Okay, so again, I'm just going to copy paste the problems here. Okay, let me do that real quick. Right, so here we want to be solving a linear system, right? So we're going to use Gauss-Jordan elimination to find the general solution for the following system. So that's the first step we want to do. Okay, so how I would do this is, well, I would convert it to an augmented matrix, right? So this is gonna be 0, 1, 3, -1. These are all zeros. Then we have -1, -1, -1, and 1. Then we have -2, -4, 4, -2, 0. Okay. And then we do everything in our power to make sure it's in reduced row echelon form. So I'm not going to do the whole computation, but basically, this is going to be 1, 0, 0, 0, 1, 0, 0, 0, 1, -1, a half, -1 half. And that would be reduced row echelon form, RREF, right? How do we know? Well, one, it's an echelon form. How do we know it's an echelon form? Well, we have this descending idea of pivots, and well, there are no non-zeros, so we can't really do that. So we know this is an echelon form. How do we know it's reduced? Well, if we look at the pivot columns, there's only one entry, which is 1, the pivot, and it's the only non-zero entry, right? For each pivot column that has a pivot or that has a leading term. Okay? Right. So yeah, that's it. Done. Done for A. Next thing we want to do, we want to give an example of a non-zero solution to the previous system of linear equations. How do we give a non-zero solution? Well, we know that one of the variables here is going to be free. How do we know? Well, we have 3 equations and 4 unknowns or 4 variables, so one of them is going to be free, right? So we could say, okay, let's just write out all the equations. Z sub 1 minus Z sub 4 is 0. That's one of them. Then we have Z sub 2 plus a half of Z sub 4 is 0. That's another one. Then we have Z sub 3 minus 1 half Z sub 4 is 0. And here we notice that the free variable is 0. So we set that to something, right? So we set Z sub 4 equal to t. So we get Z sub 1 being t, Z sub 2 being negative a half t, Z sub 3 being a half t. And that's it. So that's our general solution. Now, it's not asking for a general solution, it's asking for a non-zero solution. So t can be anything, right? So we just set t equal to 2. So z sub 1 will be 2, z sub 2 will be -1, z sub 3 will be 1, z sub 4 will be 2. So this is a general, or no, not general. This is an example of a non-zero solution, and we can even plug in more values of t. Okay? And the way we can check is just plug it in. Right, letter C. We have 3 points here, and they lie on a unique plane. Now, using your previous answers, we find an equation for this plane, and we think about the relationship between the previous system and the one you would need to solve this in this equation. So we have 3 points, and they lie on this plane. So let's actually write down our 3 points here. So we have that point, we have 1, 1, 1, and we also have -2, -1, 2. So we have these 3 points, right? And we want all of them to lie on some plane a1 x sub 1, a2 x sub 2, a3 x sub 3 equals b. So how do we do that? Well, we just plug it into the x sub 1, x sub 2, and x sub 3. So we would get something like a sub 1 plus 3a sub 3 equals b. That's one, right? And then we can do another one. A sub 1 plus a sub 2 plus a sub 3 is b. Then we can do another one. -2 a sub 1 minus a sub 2 plus 2 a sub 3 is b. And what do we notice when we were doing that? We can see that this is a system of linear equations. Now the way we can also write it like this. The reason why I'm writing it like this is because we want the right-hand side to be 0. Why do we want the right-hand side to be 0? Because we want to compare this plane. We're doing augmented matrices to what we answered in A, right? Here we see in A, after the vertical line, we have a column vector of zeros. We have the 0 vector. So we want it to be the same in this case for C. So let's actually rewrite it into an augmented matrix. This is going to be 1, 0, 3, -1, and these are all zeros. So immediately we can see they're the same in terms of size, where they have more variables than equations. 1, 1, 1, -1, -2, -1, 2, -1. Right? So that's the matrix. Now we want to compare these two guys. Let's actually do that. So you just have to stare at it for long enough, then we will see there is something going on here. Right? What do we notice here? Well, for one, we want to make, maybe they have similarities here. That's one. But maybe we want to make all of these -1, this column. So how do we do that? Well, for one, we can do elementary row operations. We can convert this to a -1. So this would be positive. If we multiply row 2 by -1, And what else can we do? We can divide this by 2. So a half of row 3. So if I divide this by 2, this becomes a 1, 2, 2, 1. Now what do we notice? So this is the same. This is the same. I'm talking about these. This is the same. This is the same. This is the same. 3, 1, 2 is the same. 3, 1, 2 is the same. 1, 1, negative 2, 0, 1, negative 1. If we look at this, right? Here, here we can see that we switch these two to get to this. We switch these two columns to get to this. Now I know in linear algebra that doesn't work, but that's the idea. We switch these two columns to get to this matrix, right? I hope everyone sees that. So if we switch, then that means if this were z sub 1, z sub 2, z sub 3, z sub 4, then we say that a sub 1 here is actually z sub 2 from the previous thing, from the previous here, right? A sub 2 in this case is z sub 1. Right? A sub 3 is z sub 3. A sub 4 is z sub 4. So that's what we notice. And we already have values for that, right? Oh, shoot. Oh, I didn't mean to do that. So we can just rewrite the whole thing, right? It's asking for a plane equation. So instead of, I'm pretty sure this was the original one. Or no, not a sub 4. I meant b. Okay. So here we can just rewrite this as z sub 2 x sub 1, z sub 1 x sub 2, z sub 3 x sub 3 is equal to z sub 4. And what's that going to look like? Well, z sub 2 is what? Well, we just plug it in. Negative 1. That's going to be negative x sub 1. Z sub 1 is 2 plus 2. Z sub 3 is 1 plus x sub 3 is equal to z sub 4, which is 2. Right? That's our plane equation. So if we plug those, or if we plug these 3 points in here, it's going to satisfy. Okay, I hope that made sense. Right. So that was the tricky part in this problem. It's getting to this point where you have to swap columns. Okay. Okay. Let's try another one here. Copying. Okay. Here we have this linear system. Now we want to find the echelon form. So how would we do that? Well, of course, we convert it to an augmented matrix. You want to find its echelon form, so I'm not going to go through the steps, but basically it's going to be like this. 9 b sub 1 minus 5 minus 17. b1 plus 2b3 b2 or b3. Right, so that's the echelon form. Done. Next, we want to I keep on having to screenshot this. That's fine. So here, we want to find B1, B2, B3 for which this system has a solution. Well, that's just this guy. This is the condition. Okay, what else can we do? Let's. Okay, these are some short questions here. Let's keep going. Do we see any shape? So what's the figure that we're gonna that it's gonna look like for the points here? Well, this is a plane, right? In R3, and it also has a normal vector. So going back from calculus 3, let's say n, 9, -5, -17. So it has that normal vector n. And it also passes through the origin. Now this is actually a problem in calculus 3. You're given something like this, and you want to find a point and a normal vector to get an equation of a plane. So that really helps, right? Here we're just doing it backwards. But you guys can check it out on how I did it in my calculus series. Should be there. Okay. Here, if I randomly pick a point, does it have a solution? Well, no, since we have a condition. We can't just pick a random point for b sub 1 to 3. That's it. If we pick these and it's not equal to 0, we pick b sub 1, b sub 2, b sub 3, and it's not 0, then we know it's not a solution, right? Easy. Okay, let's try this one. So here we consider the following linear system with A and B, unknown non-zero constants. So what are the values of A and B? Does the system have infinitely many solutions? Well, for one, how we can find this is we do our typical augmented matrix, and then we somehow find some condition, right? So here we have 1, -3, 1, 4. Okay, 2, 0, -8, -6, 6, A, B, -2. And then doing Gaussian elimination and all of that stuff, it's going to lead to this matrix. A minus 14, B plus 4, -5, -5, 3, -3, 1, 4. Okay. Now, let's do A. What values of A and B does the system have infinitely many solutions? When will it have infinitely many solutions? When one of them is a free variable, right? So when one of them has a free variable, how will that work? We can actually make both of these equal to 0 because then x sub 3 would be a free variable. So that means A should be 14 and B should be -4 so that we have a free variable and I believe the free variable is x sub 3. So there would be infinite solutions, right? I hope that's right. Yeah, that's right. Okay, what's the next one? Give an example of A and B where the system has exactly one solution. It could be anything except 14. Or no. A should be 14. Wait a minute. 3. No. A should be anything except 14. But B should be -4, right? Then we would definitely have a solution here, which might just be a 0 if I think about it, right? So there would be one solution. Yeah. Honestly, A could be anything except 14. And then we would get a solution here in this case. How do I know? Say A is 15 and B is -4. Well, that would give me x sub 3 is equal to 0, right? Because it becomes 1, this becomes 0, and then we just keep solving it. 3x sub 2 minus 5 times 0 is -5. So this would give me -5/3 for x sub 2. And same for x sub 1. So that's the idea, right? We're only going to get one solution. A could be anything except 14. Let's do C. Give an example of A and B for which the system has no solutions. Well, here A should be 14. And B can be anything except -4. Because then that would give us to this form, right? Where this is just not possible to solve. If this guy here is non-zero, would lead or would be no solutions, right? Great. I hope that makes sense. We have a couple more stuff here, but that's fine. Okay, let's do another one. When when Jake works from home, he typically spends 40 minutes of each hour doing research, 10 on teaching, and drinks half a cup of coffee. And the remaining time is spent on the internet. For each hour he works in the math department, he spends around 20 minutes on research and 30 on teaching and doesn't drink any coffee. Lastly, if he works at a coffee shop for an hour, he spends 25 minutes each on research and teaching and drinks a cup of coffee. So we have to be careful about units of minutes versus hours. Okay. So here last week, Jake spent 10 hours working from home, 15 hours working in his office, and 2 hours working at Cafe Allegro. Compute what was accomplished and express the result as a vector equation. So how would we do this, first of all? We're going to say H, our vector H is home, works from home. We're going to say D, he works at the department. And we're going to say C, he works at the cafe. Okay. Now, let's actually gather all the information we need. So we want to find here that last week Josh was spent, or no, not Josh. Jake spent 10 hours working from home, 15 hours working in his office, and 2 hours working in the cafe, right? So what would that be? What would H be? So based on the information we got, when he goes at home, he spends 40 minutes. So that's, we want to convert it to hours because we have these in hours. So that's 40 over 60. That's 2 over 3, right? And it also says he spends 10 minutes on teaching. So that's 10 over 60. That's 1 over 6. And then for the cup of coffee, he drinks a half of it. So that's 1/2, right? Then same idea. When he works at the department, he spends 20 minutes on research. So that's 20 over 60. That's 1/3. Then he does 30 minutes on teaching. That's 30 divided by 60. That's 1/2. And then he doesn't drink coffee. So that's 0 cups. Then lastly, 2. Okay. 2 hours working at Cafe Allegro. So he spends 25 minutes on research. That's 25 over 60. Or actually, yeah, 25 over 60. And if I can convert that, divide both by 5, 12, 5, 12. Same here, because he also works, what does he do? Yeah, he spends 25 minutes each on research and drinking and teaching. And he drinks a cup of coffee. So that's 1, right? And then we solve for this basically. That's what A is asking us to do. So when we solve for this whole thing, we get this 12.5, 10, 7. Now to interpret what that means, last week he spent 12.5 hours doing research, 10 hours teaching, and he drank 7 cups of coffee. Okay? So that's what that does. Okay. Let's look at B. Oh, I don't have B. Let me see. Okay, I don't know why I did that. Could have just, I could have just done this. Okay, so this week, Jake has 15 hours of research to work on and 10 hours of work related to teaching. And he also wants 11 cups of coffee because of very important research. So, how much time should he spend working from home, from office, and from the coffee shop for this week? So, for this week, he wants 15 hours of research, 10 hours of teaching, and 11 cups of coffee. So, that means we want, okay, let me do x sub 1, then we do h, x sub 2, then we do d, x sub 3, then we do c. And we want this to be equal to this guy. Okay. And I think we can translate this into a vector equation. 2/3, 1/6, half. And then this one I believe was a third, a half, and 0. Then this one was 5/12, 5/12, 1. This is equal to 15, 10, 11. Okay. So now we want to solve for x sub 1, x sub 2, and x sub 3. In other words, we're looking to see if this is a linear combination. So here's what we do. We convert them into an augmented matrix. 2/3, 1/6, a half, 1/3, 1/2, 0. 5/12, 5/12, 1. 15, 10, 11. This is the same as saying, so here I'm not going to go through the steps of these anymore, but we got it in reduced row echelon form. So this is 14, this is 12, this is 1 or 4. And there we have it. We have our solution here. So we're saying that Jake should spend 14 hours at home, working at home, 12 hours at his office, and 4 hours at the cafe to get this one, 15, 10, 11. Nice. Okay. Yeah, more stuff to do. See. Okay, this is more of a conceptual understanding of what this is, but that's fine. Okay, and then there's okay, there's about flexibility, so it's just linear combinations basically, but you apply them. This one's an interesting problem here. Okay, let's try this. I personally think this one's interesting, so we're gonna do it. Here, we're being asked to find all values z sub 1 and z sub 2 such that these two vectors do not span R3. Okay, I don't know where did z sub 1 come in? Oh, there. How do we do that? How do we know if they do span R3, given three vectors again? We have a theorem for that. And it should be that we want to make a matrix into an echelon form, and then they do span in R3 in this case exactly when there's a pivot position in every row. So that's what we're gonna do. So we want to check, so we do a matrix, right? So we just copy all of this down, and we want to check if there's a pivot position in every row. So doing all of that good stuff, we're gonna get 2, 0, 0, 1, 2.5, 0, -4, z sub 1 minus 2, z sub 2 plus 6 minus a fifth of z sub 1 minus 2. Now, how do we make sure this doesn't span R3? To not span, so to make the span of those vectors here, okay, I'm copying all of them out. Not in R3, we want this thing, z sub 2 plus 6 minus a fifth of z sub 1 minus 2 to be equal to 0. If we make that 0, then we have no pivot in the third row. And so it's not going to span R3. Right? So in other words, if and only if, so to simplify that whole thing, z sub 1 minus 5 z sub 2 is equal to 32. So if we get values for these, specifically z sub 1 and z sub 2, then the span is not R3. Okay? Right, let's try this one. Here we're given a set. So this is a set of vectors such that we have a plane. That thing is a plane in R3, has a normal vector 2, -1, 4. So here we want to find two vectors so that the span of these two vectors is that plane. How do we do that? Well, an easy thing is we just plug it in, right? Mm, Here's how we could do it though. from 2x sub 1 minus x sub 2 plus 4x sub 3, we can say this is x sub 1 equal to a half of x sub 2 minus 4x sub 3, right? Now, since we know, or okay, let me do this. Since x sub 2 and x sub 3 are free variables, so they could be anything, to be honest. Or we could really assign them in a different way. We say x sub 2 is s sub 1, x sub 3 is s sub 2, and then we would have this. I'm not done yet, but I'm just generalizing it. We have a half. So x sub 1 is going to be 1 half s sub 1 minus 2 s sub 2. Then this is s sub 1, s sub 2. Such that, oh, I did s and 2. That's fine. S sub 1, s and 2 could be any real number. So this is basically the general solution. If we want a particular solution, well, we could do it like this. Here we're just translating it. So we say s sub 1 multiplied to a half 1 0, I think, plus s sub 2. Here we do negative 2 0 1, such that these two could be anything. So that means P is the span of the vectors. Right? So a nice example, well, this is really, we got it here. An example would be this guy. These two guys. They're the vectors. And we got them from here and here. Right? One way we can check if this works is to actually plug it in. So let's try. 2x sub 1. Wait, what was this? 2x sub 1 minus x sub 2 plus 4x sub 3. Is apparently 0. So if you plug in a half minus 1, so it's going to be 1. 1 minus 1 plus 4 times 0 is 0. That works, right? If we plug in 2, negative 2, that's negative 1. 0, 4. Oh. 4. Wait a minute. 2, negative 2. Minus 0 plus 4 times 1 is not 0. Oh no, shoot, it is. Negative 4 plus 4 is 0. Oh my, I did negative 1. Anyway, yeah. So honestly, we don't really have to go through this mathematical jargon. It's just to formalize the idea. But really, we could just pick one point and then just try to guess the other two because they're free. We have two variables that are free. Right? Oh, okay. Last problem of the day. Then we should be good. So here we have three vectors, actually four, but B is an arbitrary vector in this case. So we want to use Gaussian elimination to determine which vectors B are in the span of these three. So really a way to look at it, or we want to look whether vector B is in the span of these guys. So we want to write a linear combination of the three to get B. There's a hint though that we could look back at problem 8 in conceptual problems 1. So let me just do that real quick. Problem 8, 7, oh, oh, it's here. What in the world is problem 8? 7, oh, here. Just a plane. My Am I tweaking or? Huh. Oh wait, are these the same vectors as 8? 2, 7, 8, 1. Let me see if that's a thing. Oh, it is. They are the same vectors. Oh, look at that. We already did it. We did the linear combination. We did this. We got this. So the only way for this system to have a solution is if it satisfies this idea. So this is actually the span, right? This plane is the span. That's the shape of the span that we're doing. Okay. So what I'm saying here is B is in the span if it satisfies this guy. 9B1, 5B2, 17B3 equals 0. That's when it's going to be in the span. So we can pick any B1, B2, B3 as long as it satisfies this condition here. Then we know it's in the span. Okay. Now, without further calculation, we conclude that the span of this is a plane in R3. Well, we kind of already solved it, right? And now we identify an equation of the plane. Wait, didn't we just do this? In the form ax1, bx2, cx3. Huh? Pretty sure we just did this. If we want, this is just 9x sub 1 minus 5x sub 2 minus 17x sub 3. Is that simple? That's the plane equation. Anyways, that's it for this video. I hope you guys enjoyed and learned a lot. And I'll see you all in the next one.